Well, this is Larry Moore. I'd like to welcome you to our series of presentations for the Department of Energy. The series is titled Biological Wastewater Treatment, and I just want to help folks that work with or for the Department of Energy understand biological wastewater treatment a little bit better and help you in the job that you're doing. We have 15 presentations in the series, and again, each one we're going to walk you through and do some basics today. We'll look at wastewater quality today, and then we'll get into the basics of biological treatment. Then we'll get more detailed into biological treatment, and eventually get into nitrification and denitrification and use of the BioTiger model to help you evaluate activated sludge processes and use that tool to improve process performance and also to help you save energy. So again, this is the first of 15 presentations. Each presentation will last about 30 to 40 minutes. So let's move into today's first one, which is wastewater quality. This shows you the list of the presentations. Wastewater quality today, then intro to biological wastewater treatment. We'll talk about the microbiology of activated sludge, look a little bit at biokinetics, the mathematical side of understanding biological treatment. Then we'll actually begin to look at different types of activated sludge processes. There are quite a few different types, and we want to look at those and get you familiar with those. Then we'll begin to talk about actual process control, the operational aspect of activated sludge process, and what the operator tries to do as far as controlling the process and getting it to do what we need it to do. Then we'll get into biological nitrification and denitrification, which is really important these days with regulatory agencies placing total nitrogen limits and total phosphorus limits in NPDES permits. Certainly we need to understand biological nutrient removal, and we'll talk a little bit about that. We'll get into aerobic digestion of sludge, and although that's not activated sludge per se, when we design and operate an activated sludge process, we're going to produce waste sludge, and we've got to deal with it. And one of the ways that we stabilize the sludge is through aerobic digestion, and sometimes aerobic digestion can be a big energy consumer because it takes oxygen to stabilize the sludge aerobically. So we'll get into that. And then understanding the aeration equipment is really important because in a typical activated sludge process, about 50 to 60% of the energy use will be in the aeration equipment. So we want to take a good look at that and help you understand how our aeration equipment works and how the aeration equipment can be manipulated to minimize energy consumption, because that's the greatest opportunity to save energy in an activated sludge process. And then we'll do a presentation where we look at a wastewater treatment plant, talk about saving energy, and at the same time reducing nutrient loads. And what's interesting, when we look at saving energy in the activated sludge process, often nutrient load reduction goes hand in hand with that. So they complement each other. Then we'll talk a little bit about the BioTiger model and how you use it in the measure environment. And then we'll look at actually applying the model to evaluate and simulate activated sludge processes. And we'll look at conventional activated sludge initially, and then we'll look at oxidation ditches, because there are a lot of oxidation ditches across the country and primarily used in small to medium-sized wastewater treatment plants. So those are the 15 presentations that we propose to do. So let's get into wastewater quality. Well, arguably, the most important parameter when we talk about municipal wastewater treatment, as far as defining the quality of the wastewater, biochemical oxygen demand, BOD, is, in my opinion, the most important parameter we deal with, because BOD It measures the biodegradable organic content of the wastewater in terms of oxygen equivalents. And the biochemical equation that you see here, we let Ca, H sub B, O sub C, that compound be a generic representation of the organic matter that can be in raw sewage. So we have organic matter plus oxygen being converted into CO2, water, biomass, energy, and what I like to call, you won't see this in any textbooks, but Dr. Moore likes to put it in there, OEP. OEP stands for other end products, because there are other end products that are produced that are not shown in that equation. So this kind of balances the left-hand side and the right-hand side. But the important thing to recognize about this equation is it describes what happens in the BOD bottle. It describes what happens in the receiving stream when an organic wastewater is discharged into the stream. And it also describes what happens in a biological wastewater treatment process. So it's actually two reactions in one. We have the synthesis reaction and the energy reaction, or you could call it the growth reaction and the energy reaction combined into one. But the energy reaction basically is organic matter plus oxygen being converted to CO2 and water and energy. That's the energy reaction. The synthesis or growth reaction is organic matter plus nutrients yields biomass. And the one that consumes oxygen is the energy reaction. So when organic matter is oxidized to carbon dioxide, water, energy, and other end products, that generates energy for the bacterial cell. And I may use the human body as an analogy to help you get a better feel for biological treatment. But this reaction is going on in your body right now. And this reaction is what's keeping you alive right now. You've got to have energy, and you've got to produce new cells to replace those cells that are dying in your body. And the average adult human has 70 trillion cells in their body. So again, this is an important biochemical reaction for you and for me. But anyway, we mathematically describe the BOD at any time as equal to L, the ultimate BOD, or long-term BOD, times 1 minus 10 to the minus KT. So what this equation does, Y, again, if we were to use BOD 5, then T would be 5. It allows you to calculate BOD at any time if you know the ultimate BOD. Now, we run the BOD 5, that's the standard test. And the reason we do that is because in England, when it was developed over 100 years ago, there was no point, I believe, in the Thames River that if you discharge raw sewage into the Thames River, the longest it took to get to the Atlantic Ocean or the English Channel was 5 days. So they were only concerned about that oxygen demand for 5 days in the Thames River. So they ran the BOD 5. But when we analyze oxygen demand in a wastewater treatment plant and in a receiving stream, we're more concerned about the ultimate or long-term BOD, because bacteria, they don't know the difference between BOD 3 and BOD 19. They're going to degrade the full amount of organic matter. So we're concerned about L, the ultimate BOD. And so that's how we calculate oxygen requirements in an activated sludge plant as well as in the receiving stream. A couple of types of BOD that we need to be aware of. We have carbonaceous BOD and we have nitrogenous BOD. What we need to understand is that carbonaceous BOD is simply the oxidation of organic matter to CO2 and water and other end products to generate energy. Nitrogenous BOD is done by a different set of bacteria. We call them the nitrifying bacteria, and they oxidize dissolved nitrogen, primarily ammonia. Ammonia is first oxidized to nitrite, NO2 nitrogen. And in the second equation, the nitrite is oxidized to NO3 nitrogen. And so this represents the nitrification reaction that exerts significant oxygen demand, but it may or may not show up in the BOD test. Let's look at another illustration here to help you understand this. So if you look at the bottom curve, this one, if we take raw sewage and run a BOD on it over time, and we add an inhibitor to inhibit the nitrification reaction, then we would expect to get a curve that looks something like this. That is the carbonaceous BOD removal curve. And we would get that because, again, we've added an inhibitor to inhibit any nitrification taking place. But if we don't inhibit nitrification, then we'll probably measure the BOD of raw sewage over time. Again, this is 0 days. Right in here is about 5 days. And then out here is probably 30 to 40 days. So the ultimate carbonaceous BOD will occur out at about 30 to 40 days in time. And again, that's a more important number for us in terms of determining our oxygen requirements. But if we run a BOD on raw sewage without taking any precaution, the curve will probably do something like this. It will go up, and all we see the first 6 or 8 days is just exertion of the carbonaceous BOD or the oxidation of the organic matter. And the reason for that is in raw sewage, because the wastewater is typically septic, as it moves through the sewer system, the oxygen is used up. So it goes anaerobic or septic. And the nitrifying bacteria are obligate aerobes, and so they're not going to do well in an anaerobic environment. So you don't have many of the nitrifying bacteria. And in raw sewage, you don't expect to have nitrite and nitrate because those are oxidized forms of nitrogen. So after 6 to 8 days in the BOD bottle, though, being exposed to dissolved oxygen, the nitrifying bacteria begin to develop a sizable enough population so that after about 6 or 8 days, they begin to oxidize the ammonia to nitrite and to nitrate. And that's the nitrogenous portion of the curve here. So again, when we determine the oxygen requirements for activated sludge, we got to be aware of the carbonaceous requirements as well as the nitrogenous BOD requirements. BOD data is used in a lot of ways. Again, arguably, I said it's the most important parameter we can run on a wastewater to assess its strength. But typically in medium strength municipal wastewater, I normally use a value of about 200 milligrams per liter as an estimate for the BOD5 concentration. And I typically will estimate the ultimate BOD, L, or the long-term BOD, at about 300 milligrams per liter. So what that says is typically about 68% to 70% of the BOD will be exerted in 5 days. And then the ultimate amount, or 100% of the BOD, will usually be exerted in about, again, 25 to 30 days. But we'll use BOD again to evaluate what happens in the receiving stream when we discharge an organic wastewater. Bacteria in the stream break down the organic matter, consume oxygen, and we're concerned about protecting the dissolved oxygen levels in the stream to support fish and other aquatic life. And in most states, the minimum DO that we like to maintain is 5 milligrams per liter. If we're out west somewhere and we've got a trout stream, we may want to maintain a minimum DO of 7 milligrams per liter. But we also use BOD to determine the quality of our effluent, and it's important for that as well. We often size our aeration tanks using a term called volumetric organic loading rate. Whenever we design an activated sludge process, it's important that we look at the VOLR, the volumetric organic loading rate. It is the pounds of BOD5 per day applied to the aeration tank, and it's in per 1,000 cubic feet. So it's pounds of BOD5 per day per 1,000 cubic feet of aeration tank volume. Call it the volumetric organic loading rate. It's an important design parameter. We'll use BOD to determine efficiency of plants, and then we also use it to charge our industries if they discharge high strength organic wastewater into the sewer system. For example, in Memphis, we've got one industry that discharges about 150,000 pounds a day of BOD to the Memphis sewer system. That industry by itself, in terms of BOD load, is equivalent to a city of 750,000 people by itself. Because normally we figure 0.2 pounds of BOD5 per person per day. You take 150,000 pounds a day, divided by 0.2 pounds of BOD per person per day, you get a population equivalent of 150,000 people. That's more BOD than all the citizens inside the city of limits of Memphis discharge to the sanitary sewer. And I did a rough calculation earlier, and their BOD surcharge that they pay the city of Memphis, and we have probably the lowest BOD surcharge rate in the country, but their BOD surcharge bill is about $1.4 million a month, but it's equivalent to buying gasoline at about 49 cents a gallon. It's a great deal for that industry. Chemical oxygen demand is another way that we can measure the organic content of a wastewater. Except in this test, instead of using bacteria to oxidize the organic matter, we use dichromate, potassium dichromate. Cr2O7 is dichromate. And in this reaction, at a temperature of about 150 degrees C, in the presence of silver as a catalyst, and at a very low pH because we add quite a bit of sulfuric acid, under those conditions, almost any, not all, but almost any organic compound will be oxidized to carbon dioxide and water, regardless of its biodegradability. So in the COD test, essentially what we're measuring is the oxygen equivalent of the biodegradable and the non-biodegradable organic content of the wastewater. So going back to what I said, BOD5 raw sewage about 200 milligrams per liter, the ultimate BOD about 300 milligrams per liter, and I usually estimate the BOD5 of medium strength municipal wastewater at about, the COD at about 450 milligrams per liter. So if you ask me, Larry, what approximately is the biodegradable portion of the organic matter in raw sewage? Well, what we do, we take the BOD ultimate, 300 milligrams per liter, divided by the COD, which is 450 milligrams per liter, and that's a ratio of 2/3. So what that tells us is about 2/3, typically, ballpark estimate, of the organic matter in municipal wastewater is biodegradable, and about 1/3 of the organic matter is not biodegradable. But again, the COD test, its value is primarily in the amount of time it takes. It takes us 5 days to get a BOD5 result. We can measure the COD in about 2 or 3 hours, and so we can get a much quicker estimate of the organic content of the wastewater. But normally, again, we're more concerned about BOD. So what we'll do over a period of 6 months or a year, we'll measure numerous BOD and COD values on the same sample, get a long-term approximate average between BOD5 and COD, and then we can run the COD test, multiply by that approximate ratio to get an approximate value of what BOD5 is in a matter of 3 hours. So it's an estimate, gives a way to estimate the BOD using COD as a surrogate. Theoretical oxygen demand, I know we don't normally get into this very much, but it's been very useful to me through the last 30 or 40 years. Give you an example. Had a city in East Tennessee call me about 25 years ago. ATF, alcohol, tobacco, and firearms, had seized several thousand gallons of illegal whiskey, and they needed to get rid of it. And they wanted to bring it to this municipal wastewater treatment plant. And the city said, well, we'd like to take it, but we want to make sure we know the impact on our treatment plant. Well, what I was able to do was to actually calculate the theoretical oxygen demand, and I assumed it was 100 proof whiskey, which is 50% alcohol, and using the degradation of alcohol, I was able to estimate the BOD ultimate, because that's what this equation here, the equation you see here, shows the oxidation of glucose to CO2 and water, and the theoretical oxygen demand of glucose, 6 moles of oxygen has a molecular weight of 192. 1 mole of glucose has a molecular weight of 180. So the theoretical oxygen demand of glucose is about 1.07 milligrams of oxygen per milligram of glucose. So that's an estimate again, of the ultimate oxygen demand of glucose. But what I was able to do in the case of this East Tennessee treatment plant was determine that the ultimate BOD of whiskey, and then I had made some estimates about the BOD5 to ultimate BOD ratio, and I came up with an approximate value of the BOD5 of 100 proof whiskey in the neighborhood of about 650,000 milligrams per liter. And so what I told the treatment plant, based on how their plant was designed and the loading that they were receiving now, I said, look, you can take about 125 gallons per day of this whiskey, but it has to be bled into the treatment plant evenly over a 24-hour period so that you don't organically overload your treatment plant. They took the whiskey. The federal government paid them several $1,000s to do that over a period of time. The feds got rid of the whiskey in an economical manner, and it was a win-win for everybody. It gives you an idea of how sometimes we can use theoretical oxygen demand to our advantage. Solids are also important. In municipal wastewater and raw wastewater, sometimes we're concerned about settleable solids. It's measured a little bit differently than most parameters. In most parameters, we measure them in terms of milligrams per liter. But the settleable solids test is measured in terms of volume per volume. And in typical medium strength municipal wastewater, settleable solids will be about 5 milliliters per 1 liter of raw sewage. So about 5 milliliters per liter. Total solids, which is all of the solids in the wastewater, the dissolved and the suspended solids, total solids in medium strength municipal wastewater will be about 200 milligrams per liter. Suspended solids, total solids will be about 800 milligrams per liter. Suspended solids will be about 200 milligrams per liter, and dissolved solids will be about 600 milligrams per liter. So when we measure suspended solids, what we do is we use our standard glass fiber filter, which has a retention of about 1.2 microns. Take a known volume of the wastewater, we draw it through the filter pad, and so any solid larger than about 1.2 microns will be retained on the filter pad. The solids that are smaller than 1.2 microns pass through the pad, and those are the dissolved solids, but actually they're the dissolved and colloidal solids because they're less than 1.2 microns and they pass through the filter. So the solids that are retained on the filter, we dry that pad at 103 degrees C and cool it in a desiccator and reweigh it, and then we can actually calculate the suspended solids in the wastewater. So again, dissolved solids, we'll take a sample that we filtered. Well, usually what we'll do is we'll take a sample as is on the raw wastewater. We'll put it in a porcelain dish that's been pre-weighed to get the tare weight. We'll put it on a water bath, and we'll actually heat it for several hours and evaporate all the water in the sample. And there we'll leave all of the residual solids that were in the sample, and that's how we measure total solids. So dissolved solids then would be the total solids minus the suspended solids. And then the volatile portion of the solid is a rough estimate of the organic matter. And we determine volatile solids by combusting the sample at 550 degrees C. But ballpark estimate, again, in raw sewage, medium strength, I usually use an estimate of 200 milligrams per liter for suspended solids. And on volatile suspended solids, I would use a value of about 140 milligrams per liter. Solids can be used in a lot of ways, help us to design settling basins, determine their efficiency. Obviously, suspended solids content of the wastewater gives us an indication of strength. It helps us to determine the solids loading on treatment units. An example there is when we designed the secondary clarifier and activated sludge process, a key design parameter will be the solids loading. That solids loading will be in pounds of suspended solids per day per square foot of surface area in the secondary clarifier. And so we can use solids data in the design of the treatment plant. Also, another way that solids are used in activated sludge, it allows us to determine our solids inventory in the process. Helps us calculate the age of our biomass, and that is extremely important in controlling the process, determining the age of the bacteria, and getting the process to operate in a way that will give us our best effluent quality and achieve other operating goals that we'll get into later. Solids data, we use that to design sludge digestion processes and also dewatering units. Total organic carbon is a third way that we can measure organic matter in wastewater. One thing you want to remember here is BOD and COD measure organic content in terms of oxygen equivalents. When we measure TOC, total organic carbon, now we're measuring organic matter in terms of carbon, okay? So we have to be careful about how we relate BOD and TOC, because BOD is measured in terms of oxygen, TOC is measured in terms of carbon. So what I've done here is I said, okay, let's calculate a rough approximation for medium strength municipal wastewater. What is the approximate BOD5 to TOC ratio? Well, let's let O2 represent oxygen, that's how BOD is measured, divided by carbon, which is how we measure organic carbon. And so the atomic weight of O2 is 32 grams per mole. The atomic weight of carbon is 12 grams per mole. So 32 divided by 12. And then we got to say, okay, well, what's the biodegradable content approximately of that organic carbon that's in the wastewater? Well, I've assumed that it's about 70% biodegradable. And then I got to say, well, what's the BOD5? Because otherwise we'd estimate the ultimate BOD of the wastewater. So I've got to multiply by the BOD5 to BOD ultimate ratio. So if you take 32 divided by 12 times 0.7 times 0.77, that equals 1.44. So what this tells us is ballpark estimate, the BOD5 for municipal wastewater will be approximately about 1.5 times the TOC value. And the values I again use for medium strength wastewater, I use a BOD5 of about 200 milligrams per liter, and I'll use a TOC of about 150 milligrams per liter, which is reasonably close to that ratio of 1.44. Other constituents we're concerned about, surfactants. Many industries use surfactants in their process for a lot of different reasons. These are polar molecules, and they usually one end of the molecule is soluble in water, the other end is soluble in oil and grease. And they have, again, widespread use in industry, but surfactants can cause us problems at the municipal wastewater treatment plant. In activated sludge, one of the things we try to do is create a great biological flock that's going to have good settling characteristics in the final clarifier. Well, surfactants can deflocculate activated sludge, and that will interfere with settleability and performance of the process. Sometimes certain surfactants can cause the sludge blanket to almost disappear in the secondary clarifier and adversely affect performance of the settling process of activated sludge. Surfactants can even be toxic under certain conditions, especially to the nitrifying bacteria. And here I can think especially of surfactants known as alkyl phenol ethoxylates. And those surfactants are potentially toxic to the nitrifying bacteria. And I've seen municipal plants that received a few milligrams per liter of alkyl phenol ethoxylate surfactants actually wipe out the nitrification in the process, which again may be a very disruptive impact on the treatment plant, especially if we have to meet an ammonia or total nitrogen limit in the effluent permit. Phenol is another compound we're interested in. or phenol. Phenol, if the bacteria hasn't seen phenol and all of a sudden they see 50 milligrams per liter of it, it's probably going to be extremely toxic to the bacteria, may very well kill the bacteria in the treatment plant. But if the bacteria have an opportunity to become acclimated to phenol and get used to it, then typically in activated sludge, we can handle phenol concentrations as high as about 1,000 milligrams per liter. And with acclimated bacteria, the process will readily oxidize the phenol to carbon dioxide and water. Fats, oil, and grease, another constituent I'm concerned about in municipal wastewater. Typical concentration in medium strength municipal wastewater is about 20 milligrams per liter. And usually at that concentration, it doesn't cause us a lot of problems. But occasionally, because we have a food processing industry or a petroleum plant or some other industry that discharges a lot of oil and grease, we may have problems in the sewer system, may have problems at the treatment plant because of excess oil and grease. So for that reason, most cities regulate their industries and usually do not allow a fat, oil, and grease content over 100 milligrams per liter to be discharged into the sanitary sewer. I've seen situations where food processors discharged several hundred milligrams per liter of oil and grease. That oil and grease would actually start to coat the inside of the sanitary sewer. I can think of one city in particular here in West Tennessee where we had a 36-inch sewer, and over a period of several months, because of this high FOG coming to the sewer, we built up a 6-inch film of solid grease on the inside of the sewer. So what was a 36-inch sewer now effectively became a 24-inch diameter sewer. At normal dry weather conditions, it wasn't a problem. But when we got a storm event and that excess water, what we call inflow, got into the sewer system and flows went up dramatically, the sewer line filled with water, the manhole surcharged, and the water went spewing out the top of the manhole, creating an SSO, sanitary sewer overflow. So oil and grease can create problems in the sewer system, and oil and grease can create problems at the treatment plant. Animal vegetable oil and grease is very biodegradable in our bodies and by bacteria if it's widely dispersed in the wastewater. And so it can exert an oxygen demand. In terms of petroleum oil and grease, that's oil and grease, petroleum oil and grease is not nearly as biodegradable as animal vegetable oil and grease. And sometimes petroleum oil and grease can create problems for us. So some of the problems, again, with oil and grease, mentioned, again, their ability to, if it's animal vegetable oil and grease, readily metabolized by the bacteria. Petroleum-based oil and grease, very slowly degraded by bacteria. And so, again, we're always concerned about the oil and grease content coming in the treatment plant. And another thing, fats, oil, and grease can contribute to nocardia foaming in an activated sludge process. And that is something we definitely want to avoid. Another thing oil and grease does, if it coats DO probes or pH probes or ORP probes, it can adversely affect their performance, give us false readings, and false data leads to false decision making. And then petroleum oil and grease, again, could be, under certain conditions, a fire or explosion hazard. So again, we got to be concerned about FOG coming into our municipal treatment plant. Pesticides, normally these are not a problem at a treatment plant, but I know in Memphis 30, 40 years ago, we had a pesticide manufacturer who discharged chlorinated pesticides into the sanitary sewer before they were properly regulated. Things like lindane, enrin, chlordane, and these constituents created toxicity problems in the treatment plant. And at the intake structure, because they actually were airborne, some of them, they actually created toxic conditions in the airspace of the headworks that created health and safety problems for the wastewater treatment plant workers. I believe this is correct. In the United States, chlorinated pesticides are banned for use as well as production now. Organic phosphorus pesticides, you see, those are still manufactured, carbamate pesticides. So occasionally we have to deal with these coming into the treatment plant, but again, mainly concerned because of their very high toxicity to the treatment plant, and then they may pass into the receiving stream and cause toxicity in the receiving stream. Some other problems with pesticides, again, I think we've covered them, but again, worried about impact on surface water supplies, worried about impacts to fish and wildlife in the receiving stream. So very concerned about limiting any pesticides that might come into a treatment plant. And again, generally, that's not a major concern for treatment plants, but occasionally it can be. Nitrogen is another important constituent in municipal wastewater. Nitrogen is an essential nutrient for us. It's an essential nutrient for microorganisms. It's an essential nutrient for plants. As you can see in the two biochemical equations there at the bottom of the screen, green plants will use nitrogen, usually in the form of nitrate, NO3 nitrogen, or ammonia, NH3, or NH4 plus ammonium ion. And they will use nitrogen in combination with carbon dioxide and using a process called photosynthesis to produce plant protein. Now, you and I, we also have to have protein. We get most of our protein by eating meat in our diet. But nitrogen is an essential, I call it a macronutrient, because the bacterial cell typically is about 10 to 12% by weight nitrogen. So it's an important constituent of bacterial cells. It's an important constituent of human cells. So we also have to have, again, nitrogen in our diet. And why is nitrogen important? Well, again, nitrogen allows us to make amino acids, which are used in making protein. So one of the most important aspects of nitrogen to bacteria and human beings is the ability to manufacture proteins in our cells. Now, we'll add that nitrogen exists basically in four forms in water, wastewater. Organic nitrogen, which is nitrogen tied up with carbon, hydrogen, oxygen. It's, again, nitrogen tied up in organic matter. That's known as organic nitrogen. Ammonia nitrogen exists in two forms in wastewater, either as ammonium ion, NH4 plus, or as ammonia gas in solution. And the concentration or the distribution between ammonia gas in solution and ammonium ion, the distribution is controlled by the pH of the wastewater. At a pH less than about 7.5, nearly all of the ammonia will be as ammonium ion. As in ammonium ion, the ammonia is not toxic to fish and aquatic life, or very slight toxicity. The toxic form of ammonia is ammonia gas in solution. So as the pH increases, for instance, if we were at a pH of 9 and a temperature of 20 degrees C in the water, at that scenario, approximately 82% of the ammonia in the wastewater will exist as ammonia gas in solution. 18% will exist as ammonium ion. But again, because you'd have a lot of it in the form of ammonia gas, that ammonia would be much more potentially toxic to fish and aquatic life. In raw municipal wastewater, let's talk a little bit about the characteristics there. And typically in raw municipal wastewater, we'll have two forms of nitrogen, organic nitrogen and ammonia nitrogen. As I mentioned earlier, typically we don't have nitrite and nitrate nitrogen because those are oxidized forms of nitrogen. And in raw sewage, because of the lack of oxygen as that sewage flows through the sewer system, it's an anaerobic reducing environment. So in raw sewage, typically we have only organic nitrogen and ammonia nitrogen. And ballpark estimate is we'll have in raw sewage about 35 to 40 milligrams per liter, what I call TKN, total Kjeldahl nitrogen. TKN is the sum of the ammonia nitrogen and the organic nitrogen in the wastewater. So if the TKN is raw sewage, of the raw sewage is 40 milligrams per liter, and half is ammonia and half is organic nitrogen, then if the TKN is 40 milligrams per liter, the organic nitrogen will be 20 milligrams per liter, and the ammonia nitrogen will be 20 milligrams per liter. But we're concerned about the ammonia, but we're also concerned about the organic nitrogen because most of the organic nitrogen will be hydrolyzed to ammonia by the bacteria, the BOD removing bacteria in the activated sludge process. So most of the organic nitrogen, by that equation I showed you in the very first slide, it gets converted into the organic nitrogen. Most of it gets converted into ammonia nitrogen. Okay, so very concerned about ammonia and organic nitrogen in raw wastewater. In the effluent, let's think about the effluent of an activated sludge process. In the effluent of an activated sludge process, where nitrification is taking place in the process, we would expect to have organic nitrogen, maybe some ammonia nitrogen, some nitrate nitrogen, maybe relatively high concentration of nitrate nitrogen, and usually relatively low concentrations of nitrite nitrogen in the effluent. So again, in the effluent, we may have all four forms of nitrogen that need to be considered. In terms of, again, the nutrient requirements of bacteria, normally, as a ballpark estimate, to estimate our nitrogen requirements for the activated sludge process, for every 100 pounds per day of BOD coming into the plant, we will need about 5 pounds per day of nitrogen to satisfy the nitrogen requirements of the bacteria. For phosphorus, the nutrient requirement is for every 100 pounds per day of BOD coming into the plant, we'll need about 1 pound per day of phosphorus. So those are, again, that's the ballpark estimate for nitrogen phosphorus based on the BOD load coming into the treatment plant. So again, when we design an activated sludge process, the nitrogen content, we need to be aware of that because we will need to look at possibility for nitrification occurring. And then if we have a total nitrogen limit, we'll want to design the plant for probably for biological nitrogen removal and include an anoxic reactor and achieve biological nitrogen removal. And then when we take municipal sewage sludge, it has been digested and dewatered, and we want to land apply it, then the nitrogen content of that digested dewatered sludge is very important in determining the fertilizer value of the sludge. Phosphorus, again, another important nutrient. As I said earlier, the bacterial cell is about 10 to 12% by weight nitrogen. The phosphorus content of the typical bacterial cell is about 2%. And so again, phosphorus is an essential nutrient for bacteria. It's an essential nutrient for us. The metabolic significance of phosphorus is extremely important in the generation of energy within the bacterial cell, and the same is true in our human body. It's very important in energy production. So the phosphorus, again, we need it to meet the nutrient requirements of the bacteria, but excess phosphorus discharged into the receiving stream can contribute to the excess growth of aquatic plants, or also called eutrophication in the receiving stream. The phosphorus content of digested sludge is about 1%. And typically in raw sewage, most of the phosphorus will be in dissolved form. Probably about 80 to 85% of the phosphorus will be in dissolved form. Much of it will be in the form of dissolved orthophosphate. Most of the rest will be in the form of polyphosphate, and there will be a small concentration of organically bound phosphorus as well. Sulfate is another constituent in dissolved in wastewater that we need to be concerned about. Sulfate in the raw wastewater under anaerobic conditions as the sewage flows through that sewer line. Again, biochemical reactions start to take place. The oxygen is used up, and under anaerobic septic conditions, the sulfate will be used as an electron acceptor by the facultative bacteria, and under anaerobic conditions, the oxygen will be stripped off the sulfate, and the sulfate will be converted to hydrogen gas. The hydrogen gas will come out of solution and enter the headspace. And if it's a gravity concrete sewer and hydrogen sulfide builds up in the headspace, and the hydrogen sulfide reacts with the moisture content on the top of the concrete sewer, that hydrogen sulfide reacts with water, forms sulfuric acid, and that sulfuric acid will eat away at the concrete at the top of the sewer. And that's what we call crown corrosion of a concrete sewer. So that's the problem in the sewer system. And then at the treatment plant, usually at the headworks, as raw sewage comes in, we may have excess levels of hydrogen sulfide that are extremely corrosive to our raw wastewater pumps, may be corrosive to our screens and even the equipment in our grit chambers. So sulfate, again, under anaerobic conditions, can get converted to hydrogen sulfide. Trace inorganics like heavy metals are important. Heavy metals, normally we don't think of those things as being desirable, but copper, nickel, zinc, cadmium, so forth. Bacteria typically need low concentrations of metals as micronutrients, but in very low concentrations. So in many instances, again, copper, zinc, those constituents are important. But if they come into the treatment plant in concentrations that are too high, they can be toxic to our bacteria. They can pass through into the receiving stream and be toxic to fish and aquatic life in the receiving stream. Heavy metals in high concentrations in drinking water can be toxic to human beings. You all know about the problem with, was it excess, my mind's drawing a blank now, up in Michigan. But at any rate, excess metals and water can be a problem for us. You're having a senior moment there. But the principal source of metals is from typically metal finishing facilities, but other manufacturing processes can also discharge heavy metals into the treatment plant. Well, that pretty much wraps up our presentation on wastewater quality. I hope that was beneficial to you. And again, if you have questions or comments, you can contact me at my home email address, mlarry@bellsouth.net, and I'll try to respond to your questions, as well as Tom Winning at Oak Ridge National Lab in Oak Ridge, Tennessee. You have Tom's email address. And again, we appreciate you participating in this first of 15 presentations in our biological wastewater treatment series. So thank you, and hope you have a good day.